Okay, it's just gone 12 o'clock. We should be live on YouTube. Can someone confirm you can see the title page? Yes, wonderful. Thank you, Bailey. Really appreciate that. Is the audio okay too? Fantastic. Thank you very much. Well, good afternoon. It's just gone midday. Normally we present this lecture on Thursday at 4 p.m, but I need to be off campus this afternoon. So I've brought forward the presentation. Many students I know watch the lecture at their own convenience anyway, so hopefully it's not a terrible inconvenience to students. The lecture content that would have been presented at 4 o'clock, it's been presented today at noon. So we began the week by looking at the topic of solving these nonlinear algebraic equations. And so we really shifted gear in the course to solving problems that are relevant to engineering using the tools that we've encountered along the way with Python. And today continues that journey. We're going to look at a topic called integration, and we're going to take an approach to integration that is based around numerical solutions which don't require the tools of calculus. Calculus also came up on Monday's lecture, and we aren't able to assume knowledge of any calculus for the student cohort in this group. And so the approach to integration that we take today is to apply some numerical tools using Python. And so there was really three components of the lecture today. The first of which is that I'll introduce you to the basic ideas of integration if you've not seen them before. I'm pitching the first part of this lecture at students who have never seen integration before and aren't able to use any tools of calculus that you might have seen either in high school, depending on level of mathematics you took, or indeed in at least a couple of the first year mathematics courses at university. And then I'm going to present two different methods of computing these integrals. I'll explain what they are. We're going to use two different methods of computing integrals. There are actually a range of methods for computing integrals numerically, and I've picked out what, in my view, are two of the most common types. One's called the Trapezoidal Method, and one's called Simpson's rule. And as I say, there are a number of techniques which are possible to compute integrals numerically. And I've picked out a couple. Now, I will say that if you're following along in the textbook, you'll see the red numbers there, 6.1 and 6.2, refer to sections of the textbook that you can use for reference. The treatment that I'm following today differs from the treatment in the textbook in two ways. One of which is that the textbook treatment is very thorough, although it presents two methods that are quite similar to each other, one of which is a trapezoidal method. And so the treatment that I'm giving here today is a summarized form of what's in chapter 6, but actually extends chapter 6 somewhat too, because the treatment of Simpson's rule that we present here is more that there are more details presented today than are in the text, and I give it a slightly different emphasis. And the second reason that I've chosen, and one of the reasons I've chosen to do that, is that the textbook treatment of integration actually blends together two topics, one of which is integration, the other of which is writing code that's able to be tested and verified, and which is all great, and we do it in a slightly less structured way through the course. I think it makes sense to separate those two topics. So I've really taken out the testing and verification part of the text treatment and focused on the integration. So the The basic idea of integration, and again, I'm presenting this for students who have never seen it before. If you have seen integration before, fantastic. I'll explain in a couple of slides why we might want to do this, but let's just consider the following problem. Suppose we're given a function f that depends on a variable x, and we plot it on a graph. If we're interested in the area underneath the curve f, and we want to specify some limits for x between a and between b, so it's most easily expressed using the image that you see there on the screen in front of you there. The area S is the shaded area under the curve, above the x-axis, and between the limits of x equals a and x equals b. Now, f could be quite a complicated function of x, and yet we're interested in calculating the area of the shaded sector there, S. Technically, that S is called the definite integral of f over the range a to b. And so that's the problem in integration. We call the expression S an integral, and we call the process of computing that integral integration. Few more basics. For some choices of f, it's possible to use the tools of calculus to compute S exactly. And if you've not seen it at high school, some of you may be studying Math 1002, some of you may be studying Math 1110, and you'll see calculus in those two courses, and that will give you the tools to integrate certain functions over the range a to b, and that's great. As is so often the case, though, that the functions which can be integrated are only a small subset of the functions that we might encounter in engineering applications. And that means that the direct tools of calculus fall short of giving us ways of computing the integral, the area under the curve f. The numerical methods, and I'm going to present two of them today. The numerical methods in this lecture apply even when f is difficult to integrate, or maybe even impossible. There are functions which occur very regularly in engineering, in particular in the area of probability theory, which it is impossible to come up with an expression that is the area under the curve f between two finite limits. The techniques that I'm about to show you today, each of them fit in about 20 lines of code, and you can use those methods for almost arbitrary choices of f. One assumption we're going to make here is that the f function itself is positive, so we're always looking for an area above the x-axis. If we ever wanted to find the area below, we just rewrite f as minus f, and it flips it to the vertical side, to the upper side of the x-axis, and we go again. So this assumption's not an important assumption, but I want to bring it out. So that's what we're interested in doing. We're interested in computing these areas under the curve f. Now, interestingly, if you look at this symbol here, this squiggly symbol that has an a at the bottom and a b at the top, representing the limits of integration a and b, that symbol looks like an S. Well, if you track it back 400 years, that's where the symbol came from, and the S came from the German word for sum. And we're going to see today that computing an integral is actually computed by calculating a sum of quantities, and I'll show you exactly what those quantities are. So if you've never seen the symbol before, it's an integral symbol, and you can think in your head, it's sort of a shorthand for S, for sum. There's many applications of integration in engineering, and I've listed some of them here. Area between two curves, the relationships between distance, velocity, acceleration, volumes of solids, average value of function, work done by variable force, and so on. You can read the list, and the list goes on and on. Integration is one of the most valuable and important topics that processes that need to be implemented by engineers. The reason I've highlighted distance and velocity is because I've got an example in the coming pages which focuses on that example. Some of these applications, you need a little bit of physics behind you. You need a little bit of probability theory. You might need more advanced forms of integration than we are considering today, but they all boil down to the ideas that we consider today. So I want to choose an example for you that makes sense, even if you haven't got a whole lot of physics. And so that's why I've highlighted distance and velocity in these applications, because it's probably the simplest form application of integration. So here it is. I'm going to present the particular setting for that I want you to think about, because we're going to use that as the basis for the integrals which are illustrated later in the lecture. And my claim is, I'm not going to prove it, but my claim is, if you have a function which represents the speed of an object as a function of its time, and I'll show you what one of those looks like on the next slide. So you've got a function, you've got a measurement of speed as a function of time, and you plotted what that graph looks like. Then the distance traveled is the area under that curve. So the particular setting we're going to look at is we're going to accelerate a car from rest, and we're going to drive it in a straight line. And the car speed depends on the time t. So we write that as a function, v as a function of t. And the question is, how far does the car travel in t seconds? For concreteness, we're going to look at the case t is equal to 1. Now, the claim that I'm making, if you haven't seen it before, you'll have to take my word for it. If you have seen it before, you'll recognize it. The distance traveled in t seconds is given by the following integral. We integrate the function v, remember v is car speed, and we integrate it from 0 up to uppercase T. Why those two choices of limits? Because we started at time 0 and we drove for t seconds, uppercase T. So to keep things really concrete, because I think it's really important to have a concrete example to work from, the example at the bottom of the page shows a function v of t is equal to 3t squared e to the t cubed. It looks like a complicated function. It's been chosen specifically. This is an example that comes straight from the textbook if you want to follow along. It's actually been chosen for a very particular reason that we'll touch on later. But for the moment, let's just assume that it looks like that. And you might think, what does that look like? Here's what it looks like. So v in units of, I guess it's meters per second, if we measure distance in meters and time in seconds, then the curve that you see here, starting at 0 and quickly sweeping up to about 8, a little bit more than 8 after 1 second, that curve is the speed. So you can imagine that speed being measured, for example, by a speedometer in a car. So you can measure the car's speed as a function of time. And the question is, how far does the car travel in the first 1 second? And that's given by the integral from 0 to 1, starting at time 0, finishing at time 1 second. We integrate the car speed. And the numbers 0 and 1 here are respectively called the lower and upper limits of integration. They correspond exactly to this range A and B. So in this case, it was A and B are the lower and upper limits of integration. Here, we're also integrating. We want to calculate the area under this crosshatched area, this under the area under the curve, but above the horizontal axis, and we want to integrate it between 0 and 1. Now that looks like it's a very rapidly accelerating speed. If you've never seen a problem like this before, you'd wonder how on earth could we calculate that area when the function is so complicated? We've got an expression for it, but that doesn't mean we can compute the area. That's the problem at hand. That's the problem that we ultimately want to solve. Now, as it turns out, for this particular choice of V, it's actually possible to use the tools of calculus to derive an expression for the exact area. That's why this particular V of function was chosen here on page 6. Because what it'll allow us to do, for the purposes of testing our code, is to compute a numerical approximation of the integral. It'll be a very accurate approximation if we set it up correctly, and we can compare it with the exact answer. That's why that particular value of V was chosen. If you've never seen calculus before, you might be surprised that such a complicated expression could in fact have an expression for the integral of that function, which is exact. Such is the case, that's the power of calculus. So that's the problem at hand. How do we go about solving it? So now we switch to solution methods. Everything up until now in today's lecture has been setting up the problem, motivating it, giving you reasons for wanting to understand what integration is, and talking about what it means and how we represent it in symbols. The first of two methods I'm going to present for you today is called the trapezoidal method. And the idea of the trapezoidal method is that we approximate. We're not going to do things exactly, but we'll get very close. We're going to approximate the area under the curve by approximating the curve, or the area under the curve, with 4 trapezoids. Now you might say it looks like 3 here. There's actually 4. If you zoom right in, there's actually a little trapezoid that approximates the curve between 0 and 0.2 seconds, and that's in black. So I've deliberately chosen the font colors here of black, green, red, and blue. They are the 4 colors of the trapezoids: black, hard to see, green, red, and blue. And you can sort of just see visually, if you look carefully, you'll be able to see a trapezoid, and I'll show you what a trapezoid looks like in isolation on the next slide. But you can see here that we've chosen 4 trapezoids to sort of fit close to the curve, this rapidly accelerating black solid line. The smooth line that you see here is being approximated, or the area under that curve is being approximated by these 4 trapezoids. So the idea of the trapezoidal method is that if we choose the trapezoids appropriately, I'll show you what that means in just a slide or two, the area of the trapezoids is easy to calculate. And if we have enough of the trapezoids, we can add up the area of each of them that fits as an approximation to the curve, and we get an approximation to the integral. So that's the basic idea. In fact, that's the basic idea of all forms of numerical integration, to replace areas under curves by areas of simpler functions for which we can compute the area underneath them exactly. Now, one thing that's a little curious, it's done deliberately, but that's a little curious about this particular example, is that the trapezoids here are not all of equal width. The first one extends from 0 to 0.2. The next trapezoid extends from 0.2 to 0.6, so width of 0.4. And then the red and the blue are both 0.2. Usually when you're doing numerical integration using the trapezoidal method, you use trapezoids of constant width. And that's what we're going to do today. There's no real point. Well, there can be, but there's no, at least to get started, there's no good reason to use irregularly widths that are irregular. So that's the basic idea of the trapezoidal method in an image. And the reason why that method works is because the area of a trapezoid is easy to calculate and it's easy to calculate exactly. So the general form of a trapezoid looks a little bit is a little bit different to this one, but this is a special case, and it's the case that applies to the problem we're trying to solve here, numerical integration. So suppose we've got a trapezoid, it's four sides, it sort of looks like a wonky rectangle. The width, the horizontal width across the bottom is h, and we're going to use that terminology throughout the rest of the lecture. So it's width h, and the two heights, remember I said it's sort of like a wonky, irregular rectangle. The two heights are uppercase A and uppercase B. And I've indicated the vertices of these upper vertices with red dots. The way we're going to apply the trapezoidal method to numerical integration is to choose these red dots. If I go back a slide, the red dots will be the function value at those 2 points. So for example, let's choose the blue trapezoid here. It's being chosen to approximate the area under the curve between time 0.8 and time 1 by making the trapezoid vertex at time 0.8 exactly equal to the function value at that time, and the upper vertex is equal to the value of the function at time 1. So you can see it's not perfect. The trapezoid's not capturing exactly the curve here. We're going to get around that problem by choosing many trapezoids, not just the 4 that are presented here. Okay, so the area of a trapezoid is given by this expression. And the way I think of it, it's the width times the average of the two heights gives the area of that trapezoid. Not hard to prove that. Take my word for it if you've not seen it before, but the area of this trapezoid is the width times the average of the two heights. Okay, here we are. Oh, by the way, I've posted the code to reproduce this curve in the lecture code channel, and I'll pop it in Blackboard as soon as we're done. I'm not going to focus on this code because it uses a couple of language features that I don't want to dig into here. Very happy to share the code with you, and you can use them to your heart's content. I don't want to get into the language specifics about how I coloured a region under a curve, but that's what the code does for you, and you're absolutely encouraged to experiment with the code, but I'm not going to give you the code listing here. That's not important. What is important is the shape and the image that you see in front of you. And what does that image show you? It shows you the curve, the car speed v as a function of t. It shows 4 trapezoids, and then the equation might look a bit scary, but if what it says is the area under the curve between 0 and 1 is made up of the area between 0 and 0.2 plus the area between 0.2 to 0.6 plus the area between 0.6 and 0.8 plus the area between 0.8 and 1. So this is a property of integrals that's really fundamental. It says areas can be broken up into non-overlapping areas, which when summed together give you the total area. Sort of common sense, but it also requires, it's a proof that you'll cover in mathematics, if and when you need it. What I want to draw your eye to, though, is that this is not an approximation. This is exact. This says the area under the V curve is equal to the area under the 4 in the 4 regions. Now we come with an approximation, and again I've used color coding here to represent the parts of the equation that correspond to the colors in the graph at the top of the page. So let's focus on the one in blue. The area under the V curve between time 0.8 and 0.1 is approximately, that's what this double squiggle here is. It's approximate, it's not exact. It's only an approximation. The area under the V curve between 0.8 and 1, time 0.8 and time 1, is given by the width, H4, which is the width of this blue panel, times these two numbers divided by 2. Remember how I said it's the average of the two values. So it's the average of the function v at 0.8 and the value of v at time 1. That's what v at 0.8 and v at 1 means. And then take the average of them. And likewise, the red area, the trapezoid, is equal to the width of the red zone plus the average of the function values at the two extremities. Likewise in green, notice for green that the limits are 0.2 and 0.6. So there's a width there of 0.4, the difference between those two numbers. Again, just to show for illustration, in practice, numerical integration, including the trapezoidal method, the code I'm going to give you in a page or two, usually uses constant widths. But there you go. So what this equation says is a lot of mathematics on this slide, but what it says is the area under the V curve between 0 and 1 is approximated, that's what the double squiggle means, is approximated by the area of the 4 trapezoids. Keeping in mind, again, that the first trapezoid is really hard to see. It's down here if you zoom right in, you can see it's a trapezoid, but between 0 and 0.2, it doesn't make much of a contribution to the area. Why? Because when the car's moving slowly, the area under the curve, meaning the distance traveled, you don't travel much in the first 0.2 of a second. You travel much more in the final 0.2 of the second, which is the area in this blue trapezoid. So just for reference, I've got the H's there. They're the widths of the 4 trapezoids, 0.2, 0.4, that's the green, plus 0.2, plus 0.2. Okay. General trapezoidal method is we want to approximate an integral between the limits of A and B by n trapezoids of equal width. And so instead of choosing the particular numbers that you've seen with this concrete example, we're going to choose constant width intervals that run between, for example, from x0 to x1, x1 to x2, x2 to x3, x3 to x4, and so on up to xn to the -1 up to the xn. The first time we run the code that you're going to see very shortly, we're going to start with 4 panels, 4 equally spaced panels. And then we're going to bump up n and see that as we make n larger, namely we take more and more trapezoids of smaller and smaller width, we get closer and closer to the right, to the exact answer. So this is the general case. In practice, we might have to choose n is equal to 100 or even 1,000 in order to get the rectangles sufficiently narrow that the error introduced by having the trapezoidal approximation to the actual function is only small. Now, what I want to do is I want to go through a little bit of mathematics in order to get a simplified answer that we can easily write the code for. So I've done this in stages. This property that you see here, it looks like pretty fancy mathematics. What it says is the area under the curve F between A and B is actually written down as the sum of these panel contributions. And for this equation to be true, the x0 here would have to be equal to the lower limit of integration A. And right at the other end, the upper limit of the final integral, xn, would have to be the upper limit of integration B. So that says the area under a curve is equal to the area of the under different panels. No approximation. That's if we're integrating, we're doing the integration in little panels. But still, it might be that F might be really complicated and very difficult to integrate over those panel widths. So what we do is we replace each of them with their trapezoidal approximation. So I just want you to focus on the first one. What this says is that the integral of the function f between the limits of integration x0 and x1 is equal to, remember the equation for the the area of a trapezoid, it's h, the width, times the average of the function values at those two limits, the upper and lower limits. Now, the expression that you see here is only true if the area is divided into n chunks, and each of the variables that each of the widths is h. It's the total area of integration a to b divided by n. We'll see a concrete example in code shortly. Now, what you'll notice, if you look carefully at this expression on the screen here, you'll see in the first trapezoid, in the numerator, there's an f1 term, f of x1 rather. And that same term occurs in the first entry of the second trapezoid. So see if I can, don't know if I can highlight. This fx1 also occurs here. And likewise, f of x2 would match up with the first term of the next trapezoid, and so on. And if we collect all those terms together and do a little bit of rearranging, we get a nice compact form, which says that the integral from a to b of f of x is equal to the panel width h divided by this expression in the square brackets. If you look at it closely enough, you'll see that the f of x0 term occurs with a fraction of a half. That comes from this term at the front here. And the very final value also occurs with a fraction of a half, corresponding to this term at the end. And all the other terms occur f of x1, f of x2, f of x3, f of x4, and so on. They're all lumped together in the middle where we sum them all up. So there's a little bit of mathematics involved in putting the expression in the form that you see in the blue equation, highlighted in blue to draw your eye to it. And what that does, it really simplifies the implementation of the trapezoidal method in Python code. So just to step back to look at the general case for just a moment, it's often a good strategy, not always possible, but it's often a good strategy to spend some time simplifying the expression with a little bit of mathematics to then simplify the writing of the code. And that's a great, what you see there in front of you is a great example, because what we've got here is a summation between the two curly parentheses that's beautifully suited, perfectly matched to use a for loop or a for loop in a bit of Python code, because we know we're going to do something, we're going to add something together, and we might have to add 1,000 numbers together, and we can set up a loop in Python which does that calculation, and then add on at the front, add on something in the tail, and we've got an approximation to our integral. Okay, enough of the mathematical setup. Let's look at the code. Again, I've posted the code in the lecture code channel. I'll post it on Blackboard as soon as we're done here today. So the key things I want to draw your eye to are that we're going to use the NumPy function. It's line 1. In line 3, we define the function that we want to integrate. This is exactly the expression that we saw at the very start of today's lecture, 3t squared e to the t cubed. Here's where all the action happens, or most of the action. In lines 6 through to 12, we've got a function written in Python which implements the trapezoidal method as a function. So it takes in 4 arguments, takes in the function that we want to integrate, the lower limit of integration, the upper limit of integration, and n is the number of panels. So we're going to start down here in line 14 with 4 panels, but then we'll experiment live with it, and I'll show you what happens when you increase the number of panels. And here you see most of the action happens in this for loop that runs over lines 9 through 11. what this expression is doing is adding up all the terms that occur in this inner sum, the function values from 1 up to n minus 1. And so here it's done. We're calculating f sum as a running sum plus the function values f of x, and this the for loop parameters here in the range 1 and 1 means we start at 1, we finish before n, namely n minus 1, in steps of 1. So this for loop here in line the header for the for loop in line 9 is exactly setting us up to perform this summation here that I've highlighted on page 11, where the indices run from 1 up to n minus 1. That's exactly what the for loop does. So the trapezoidal function takes 4 input arguments, and what it returns is this expression that I've highlighted here on line 12. It returns the sum that we computed through the for loop in the middle, plus a half of the function value at the start, and plus a half of the function value at the end, the upper and lower intervals. And that's exactly what this expression here is in blue. And we multiply it by h, and h are the limits of integration, or the difference between them, divided by the number of panels. In line 14, we actually call a trapezoidal function with function v, lower limit 0, upper limit 1, number of panels. And then in line 16, I didn't present this expression before, but this is the exact expression. I don't expect you to know where that comes from. If I ever needed you to use an expression like that, I would give it to you, because you're not expected to know calculus coming into this course. So let's run the code. Let's run the code. Here's the code. It's a trapezoidal function in lines 6 to 12 where all the action happens. Lines 3 and 4 define the function, and we actually call the trapezoidal function down here in line 15. So let's run that code now. And what we see is that if we use 4 subintervals, keeping in mind that the exact answers are printed down here, we've got a print statement that prints the trapezoidal approximation, is only an approximation, and the exact expression on the following line. So whereas the exact answer is about 1.718, with 4 subintervals, we get an approximation of 1.92. So that's about a 10% error. But we can do better than that. Let's make 10 panels and then run the code again. And now we see when we've got 10 subintervals, we get an answer of 1.75, where the actual answer is 1.71, 1.72. So by increasing the number of panels or subintervals, we've decreased the width of the trapezoids, and we've got more of them. So we would expect a better approximation. Sure enough, that's what we see. What happens if we make 100 panels? The approximation is 1.7186. The exact answer is 1.782. So we're getting closer and closer. Let's go crazy. Let's make 1,000 intervals, run the code again, and we get 1.7182, 1.7182. It's right to about 4 decimal places. So again, as we make more trapezoids, they get narrower. We get a better approximation. There's less error in approximating the function with the top edge of the trapezoid, and so we expect a better approximation. So let's go absolutely crazy and put 10,000 panels in, see what happens. We get an answer that's right to about 6 decimal places. So that's pretty good. Now, while in this particular example, we know an exact answer, in general, we don't. And so one of the things that's good to do when you're writing code is to test your code in a situation where the exact answer is known. Even better, test it with a few different examples where the exact answers are known. And if you're getting answers that are close to the exact answer, very close to the exact answer with your numerical method, you'd be pretty confident that it would work for an arbitrary function f. That line of reasoning is what the textbook goes into in more detail. I don't want to cover it here, but that's sort of what the textbook is done in this case. So that's really good. We've got a method that works. I've got a little bit of commentary here for you to work through at your own time. We've covered all the points there in our discussion. Truth of it is, for numerical integrals or so-called one-dimensional integrals or integrating scalar functions like we've done here, the trapezoidal method is going to work pretty well just about all the time. I'm going to show you a second method now because it's not that hard to implement, but it will give a better answer, meaning more accurate. That means that it's faster. And that means if you have to compute lots of these integrals, there's a time advantage. But the truth of it is, the trapezoidal method and about 4 or 5 other methods, which some of them we might experiment with in next week's, the week after next lab sheet, they all work pretty close to the same. They all approximate the function with functions that are easy to integrate and choose panel widths that are really small and just use the power of the computer to add up lots of numbers. But if you locked me in a room and said, you're not getting out until you've computed an integral to 6 decimal places of any scalar function we give you, I'm going to choose a trapezoidal method every day of the week. It works. The code fits into the whole code fits into 20 lines. The actual implementation of the code fits into 6 lines, 7 lines. And all you need to do is just increase the number of panels to get a higher level of accuracy. It's a Butte method. It's relatively simple, and it works. Here's another method. I introduce it because you might see it in mathematics. You might have seen it elsewhere. I think in some cases you might have even seen it in high school maths, depending on what level of mathematics you studied. Similar premise to the trapezoidal approximation, except that starts from a different assumption. And the assumption here is that the curve over which is the function we want to integrate over the limits a to b, we can approximate, that's written in the blue curve, and that's the function f of x here. So-called Simpson's rule, or sometimes called Simpson's method, approximates the blue curve by a parabola. And we're going to specify 3 points on the parabola. We're going to insist that our parabola p of x takes on the same value as the blue function. So the red curve takes on the same value as the blue function at 3 points. The upper and lower limits of integration, the a and the b, but also the midpoint. So this midpoint, m is for midpoint, it's the average of a and b. And you might recall from high school that if you specify 3 points on a parabola, you've uniquely nailed that parabola down. So Simpson's rule starts from the approximation of an arbitrary function by a parabola. And the parabola intersects the function at the upper and lower limits of integration plus the midpoint. What good is that, you say? Well, the area under a parabola between those limits of integration a and b can be calculated exactly. and the expression in blue at the bottom of the page captures that. Talk about it in a moment. Notice what I'm not saying. I'm not saying that the area under the function f is calculated exactly. No. I'm saying the function f can be approximated by a parabola, and the area under the parabola can be computed exactly. And you would hope, if the function f is fairly well behaved, if it doesn't oscillate around much between the two endpoints, then you would hope that the area under f is pretty close to the area under P. That's what the idea behind Simpson's rule is. Now, I'm not giving you the proof. The proof's not relevant to us in this course. You may have seen it at high school. You may have seen it in mathematics studied at university. You may yet see it in mathematics studied at university. But the area under a parabola between A and B, provided that parabola intersects coincides with the function value f at the upper and lower limits of integration and the midpoint, can be approximated by this expression in blue at the bottom of the page, which says that it's the area under f between the limits A and B can be calculated as the function value at point A, namely the height of this first dot, plus the function value of B, namely the height of the third dot, plus 4 times the function value at the midpoint, the average of A and B, and the whole lot summed up and multiplied by the range of integration, B minus A, divided by 6. That's Simpson's rule. And the way that we can apply it in something sometimes called composite Simpson's rule, if we want to apply Simpson's rule to a really high accuracy integration, we do just what we do for the trapezoidal rule and apply Simpson's rule on each subinterval. And here we've defined the subinterval of width h as being the total width of integration from A to B, or the difference between those two numbers, divided by the number of panels. So we can break up the area of integration into these n subintervals again, and then we apply Simpson's rule on each of those panels separately. And that's called Simpson's rule, or it's actually it's more accurately called the composite Simpson's rule, because it composes the total integral is composed of the sum of the Simpson's rule applied to each of the subintervals. Here's the Python code. We're going to run it live in just a moment. Simpson's rule looks very similar. The code set out is deliberately very similar to the trapezoidal rule. We're going to use NumPy. We define the function we want to integrate. Here's the implementation of Simpson's rule. It fits in, 8 lines of code, including a comment. So again, fits in 7 lines of code. The core of this algorithm is the running sum computed in line 13. And if I highlight this line of code here now in line 13 of the code, you can see it's a running sum. We're using this plus equals operator. And let's look carefully. It's f at the lower limit of integration plus f at the upper limit of integration plus 4 times the function evaluated at the midpoint of the limits of integration, where we're integrating over each of the subintervals, and then we're summing them up, all the results. So this, what you see here in the highlighted equations, lines 9 to 13, we're summing up the results of Simpson's rule applied to each of the subintervals that are broken up across the actual area region of integration that we're interested in. And the rest of it, same format as before. 4 panels to start with. We call the function in line 17, and we've got the exact answer to call on in this particular example because of this very particular choice of V. In general, we don't have the exact expression, but it's super useful for testing. So let's run it live. Simpson's rule, this is exactly the code that you've just seen on the slide. Function defined in lines 6 to 14, function to integrate on lines 3 and 4. And we're going to start by calling it with 4 panels. Run Simpson's rule, and we see that even with 4 panels, 4 subintervals, we get a pretty close answer. We get an answer that's correct to 2 decimal places with just 4 subintervals. So as a general rule, as a general guide, for the same number of subintervals, Simpson's rule is going to do a better job than the trapezoid. And the reason is that the parabola is more flexible and more able to fit the shape of the function, even when it's varying a bit over the limits of integration, in contrast with the trapezoid, which has to fix the beginning and end points with a straight line. So let's bump up the number of panels now. Let's bump it up to 10 panels. Run the code again. And we can see that we really are getting a very accurate answer. It's probably right to within about 1 part in 1,000, maybe 1 part in 10,000 with just 10 panels. And if we have 100 panels here now and run it, we get an answer that's correct to 8 decimal places. So that's 1 part in 100 billion, 100 million, just with 100 panels in it, and it takes next to no time. So very quick to calculate, and we need only a fraction of the number of panels. On the other hand, the calculations inside Simpson's rule are a little bit more time intensive than for the trapezoid method. This would be a good type of code to test with some of the tools we looked at on Monday's lecture, which looked at how you time, how long pieces of code to take to operate, take to execute. And that is just about us done. There's some commentary there, nothing that I haven't said in words along the way. And we're done. So in summary, we looked at what integration means. I mentioned a number of applications. Some of those the full power of them won't become apparent for maybe a year or 2 of your study, but I can guarantee that at some point in your course of engineering study, that you will use integration. It's one of the most common techniques, mathematical techniques that are applied to the study and practice of engineering. A couple of methods presented: trapezoidal method and Simpson's rule. Trapezoidal method is covered in some great detail in the textbook. Simpson's rule is touched upon in the textbook, but not covered in depth. I thought it was useful to show you 2 different methods. I also thought it was worthwhile showing you Simpson's rule, which sort of it shows you that if you use slightly more sophisticated mathematical techniques, in this case, fitting a parabola instead of fitting a straight line across the subintervals, then that pays off in computation time. It's probably 10 times faster than the trapezoidal method, simply because you need maybe 1/10 of the number of panels. So again, if you're following along in the textbook treatment of numerical integration is excellent. It's just more than we need in this course. It integrates other aspects that I don't really want to cover in the context of this material, along the lines of code testing. So we're just pressing up against the hour. So at this point, I'll thank you for your attendance. If you're attending live, thanks for joining me. If you're watching this afternoon, Sarah will be in the Q&A chat, and Sarah's also kindly offered to watch the Q&A channel this afternoon for students that are following along this afternoon. All the code's been popped into the lecture code channel in Discord. And as soon as we're done, I'll put the lecture slides and the 3 pieces of Python code on Blackboard. Until we catch up on Monday, I'll say bye for now.